Okay, everyone. So today we're looking at calculations involving weak acid and weak base situations or equilibrium. And up till now, I believe we've only really been dealing with strong acid and strong base and mixtures of strong acids and strong bases. So up until now, right, let's say we had hydrochloric acid, right? So when hydrochloric acid is in water, right, we have, of course, proton donation. So we have hydronium and chlorine ions as a result, correct? So because this is a strong acid and it will 100% ionize, essentially whatever the concentration is of the acid would be the same concentration for the products, right? So let's say, for example, we had an acid concentration of 2 moles per liter. The concentration of hydronium would also be 2 moles per liter because all of it is becoming hydronium. But what we're going to find now is when we're dealing with weak acids and the same story goes with strong bases, right? So whatever the concentration is of the strong base, you can determine the hydroxide concentration based on the mole ratios. However, once we get into now weak acids and weak bases, we have an established equilibrium process because remember, we will not have 100% ionization. In fact, it's somewhere between that 1 and 99%, which is what an established equilibrium is. So what that means is if we're trying to determine the hydronium concentration for a weak acid solution so that we can find, let's say, pH, we would have to set up a K expression and determine what that would be at equilibrium. Right? So let's say, for example, initially I had 2 moles per liter of our weak acid. Well, now we would have to do, okay, well, 2.0 minus X, and then our products would be plus X, right? So we would have to set up an expression, which is where our Ka is going to come in order to determine what our X value is. So when you're asked to determine the pH of a weak acid or weak base solution, you have to create an ice table because it's in equilibrium essentially. Okay, so we cannot use mole ratios. That's one of the main differences when you're approaching strong acid, strong base calculations versus weak. Right now we have an established equilibrium, so we'll have to set this up. So a Ka expression, just like any other time, maybe I'll clean this up so you can see this a little bit more properly. But just like any other time we set up a K expression, right, it's going to be products over reactants. And remember, we're not including water because it doesn't have a concentration here. So you would have your ions, your product ions over the original weak acid. So this is the acid ion constant, or essentially your Ka, right? K is always K, it's just being more specific. It's K for a weak acid equilibrium. Okay, so now getting into different types of calculations that you are going to come across here. There's a few things to keep in mind. So the first thing is, anytime you are given concentration in an equation, okay, so let's say, you're told that you have a 2.0 mole per liter of acetic acid, right, which is a weak acid. You are always to assume that that is the initial concentration. So when you go to set up your ice table, the concentration of your weak acid or weak base is always your starting point, your I concentration. If they give you the pH or pOH of that solution, okay, pH and pOH is already in equilibrium. So for example, if it says the pH of an acetic acid solution is, let's say 5.2, this would automatically mean that that is at equilibrium. Okay, the question will not say that, but if you're given pH or pOH, it's assumed to be equilibrium. Okay, concentration is initial, pH, pOH, equilibrium. Okay. Number 3, if the question is asking you to determine the equilibrium concentration of hydronium ions, right, you would have to create an ice table. So we've already talked about this. The initial concentration is not enough to go by to solve hydronium because you need to have, since you have equilibrium happening, you would need to set up a Ka expression. So this is something we've already talked about. Number 4, if you are not given the Ka value, you actually have a list of Ka values that are in the back of your, inside the back cover, like at the back of the book. Let me give you the page number exactly since I have that with me. So it's actually on page 521. We've looked at this already when we first talked about weak acids and weak bases. Remember, it's the table of relative strengths where they list them according to the strength. So it's on page 521, and on D2L, it's in that separate PDF. There's a PDF of the appendices that you can look at there. Okay, now keep in mind, right, this is always in reference to 25 degrees Celsius. So if the question tells you that it is at a different temperature, then that means you cannot look up the value. You probably are going to be asked to calculate it. But if it does not tell you a temperature, you can assume it to be 25 degrees. Okay. If you have a polyprotic weak acid, okay, so what we mean by polyprotic is a weak acid that has more than one hydrogen ion. So for example, carbonic acid. So carbonic acid is a weak acid, but it actually has 2 hydrogen ions that it could lose, right? So the first ionization process, and remember, whenever we, why is my H is so weird? Remember that whenever we move a proton, it's always, and we've done this before, one at a time. Right, so even though carbonic acid has more than one to lose, you only really move one over to create hydronium and bicarbonate ions, essentially. So if you're asked to determine the pH of something that has more than one hydrogen ion to lose, we always only refer to the first proton leaving. Okay, the reason why is because after carbonic acid loses a hydrogen ion, even though bicarbonate has one more hydrogen ion to give away, it's actually much weaker after that first ionization. So what happens is, even though this HCO3 -1 will continue to react and lose it a second time in a different process, we can consider that second hydrogen ion to be insignificant. Just because if you're determining the pH, the concentration of hydronium coming from this first ionization is going to be much, much larger relatively to this second hydronium concentration that's produced. So just to give you an example, I'm going to I'll continue, ignore 6 for now, we'll come down here, right? So what I mean by that is, let's say HCO3 is going to react again. Of course, it's going to be in solution, so it will do this. Right? So this concentration is going to be much lower than the first one. So much, in fact, that we can basically consider this to be insignificant. Okay? Just so you are aware, each of these processes have a different K value, right? Sometimes they're referred to Ka1 and Ka2. So it's like the first hydrogen that's being ionized and then the second one. So Ka1 is always larger than Ka2. Let's say you have an example of phosphoric acid, right? They have this weak acid has 3 hydrogens that it will actually lose. So it has like a Ka1 and a Ka2 and a Ka3. But again, we only ever consider the Ka1, which is the first hydrogen to leave, because it becomes much more weaker as those processes continue. Okay, so those K values are not equal, and you will only ever consider the very, very first one to leave. Okay, sometimes students get confused and they want to calculate both hydroniums and then add them up. It doesn't really change the pH a whole lot. Okay, the last point to consider, so these are just, again, these are things to keep in mind as we are working through problems, because they're going to help you to organize the information that you're given and kind of like what you're looking for. So each equilibrium is only with one proton being donated. So it's always a 1:1:1 mole ratio. So we've already mentioned this. So when you lose a proton or when the water is gaining one, you only ever move one at a time. So your ratio here, right? Imagine like my coefficients, it's always the 1:1:1:1, right? But we normally don't care about water. Okay, so let's talk about percent ionization, just to remind you that you have percent ionization is really looking at the amount of product versus the amount of initial, the initial amount that you began with, right? So when you have 100% ionization, that essentially means you have all product and very, very little or almost nothing for your initial amount. Okay, but we know that for weak acid equilibriums, it's going to be somewhere between that 1 and 99%. Okay, so it's important to note that the assumption is not always justified when we're talking about percent ionization of a weak acid. So what do I mean by that? This is literally going back to, if you remember, we learned about the 1,000 rule. So if your initial concentration is at least 10 to the 3, which is 1,000, times larger than the Ka value, the assumption is valid. And what we're talking about here is the assumption of removing X, right? So when you are adding X or subtracting X, you can remove X if you deem it to be essentially so small that it is insignificant towards your original value. Okay, so you're going to see this will come up when we go and do our calculations. Okay, but in other words, kind of another way of saying it is that if you have a percent ionization of a weak acid that is less than 5%, you can basically ignore that X value, right? So these are just some examples, right? So if we're looking at percent ionization, these first two, the percent ionization is so small that if we had 0.15 minus X and 0.015 minus X, we can get rid of the X value because it's so small that it's considered to be insignificant. However, if you have a value that is not 1,000 times greater than the initial, or I should say the initial is not 1,000 times greater than the Ka value, that would indicate you have an X value that would have to stay put. You would not be able to remove that. So we saw this rule before when we did the common ion effect. So the same thing is going to happen here where, in this case though, instead of adding X, we're removing X. If you have the 1,000 rule that is applicable, you can get rid of X. However, if not, you would have to factor through and determine your X appropriately. All right, so let's start taking a look at some problems. Actually, we're coming close to the end of this first part. We'll start looking at these in part 2.